solve one problem on heat transfer through a combination of cylinder and sphere by using electrical analogy method. We will read the given question. A storage tank consists of a cylindrical section that has length and inner diameter of L is equal to 2 meter and D is equal to 1 meter respectively, and two hemispherical end sections. Tank is constructed from 20 mm thick glass and is exposed to ambient air for which temperature is 300 Kelvin and convection coefficient is 50 watt per meter square Kelvin. The tank is used to store heated oil which maintains the inner surface of tank at a temperature of 400 Kelvin. Determine the electric power that must be supplied to the heater submerged in the oil. If the prescribed conditions are to be maintained, radiation effect may be neglected. Let us understand the given question with the help of diagram. It is given that the storage tank is having cylindrical section enclosed with two hemispheres. We will draw here the cross section of the storage tank. Now for this cylindrical section, length and diameter is shown. So this middle section is for the cylinder and whose having length L is equal to 2 meter and diameter we have to show with the help of this height, that is 1 meter. Now at the end of the cylinder we have to draw the cross section for the hemisphere. So how to draw? So for the end we have to select here one center point for this height, and from this we have to draw the half circles that will indicate for the hemisphere. So for that we have to take radius is equal to 0.5 meter and we will complete these circles. Now this storage tank is made up of glass material and which is having thickness 20 millimeter. So again we have to show the thickness for this whole cross section of the storage tank for 20 millimeter. Now inside the storage tank there is the heated oil, and if we observe the question, the inside surface temperature is given, that is we will say Ti is equal to 400 Kelvin, and then the outside ambient air temperature T air is 300 Kelvin is given with convective heat transfer coefficient H is equal to 50 watt per meter square Kelvin. Now we have to solve this question by electrical analogy method. So we have to first find out how many resistances are involved when the heat transfer process is taking place from this inside surface temperature to the ambient air. Now this is the combination of cylinder and sphere. So we have to consider the different resistance. Why we are going to consider the different resistance? Because the formula to calculate the resistance for the cylinder as well as sphere is different. Now if we observe the heat transfer process, so heat will be getting transferred from this heated oil to the ambient air. So we have to show the direction of the heat flow. Now this heat will flow in cylinder, that is from the surface material of the cylinder. So I will show from this heated oil, heat will be transferred Q in this direction. Now at the same time heat will flow from this heated oil to the ambient air through this sphere also. So we will show here this Q in this direction. So we can say that this Q is that is the heat will flow in cylinder and at the same time heat will flow through the sphere. That means these are the two parallel way the heat is flowing from the different cross sections. Now we will find out the resistance. So when the heat is transferred from the surface of the cylinder, that is from this temperature Ti is given, then here is the glass material. So what is the resistance for the conduction heat transfer process? We will consider here as a R1. And then again from this outer surface of the cylinder heat is transferred to the ambient air with convective heat transfer. So for the convective heat transfer we will consider the resistance R2. Now this is about the cylinder. Now we will move for the sphere. So from sphere also, here is the inside surface temperature is given. Now from this inside surface, the heat is transferred through this glass material, so which is having resistance R3. Now this is about the hemisphere we are talking. Now again from this outside surface, again the heat is transferred through the convection process, and the resistance we will consider R4. Now the same resistance is getting transferred from the second hemisphere. So we will say this resistance will be R3 and here is R4. Now here 2 times R3 is there and 2 times R4 is there. Now if we combine these two hemispheres, then it will become complete sphere. So while we are going to calculate this R3 and R4, we will use the formula for the heat transfer through this sphere, because this combination will become the complete sphere. Now we will move to draw the electrical analogous circuit. So what is the temperature? So here the initial temperature is Ti, because from the surface temperature heat will flow to the direction towards the air. So here Ti minus T air. So all the heat transfer process is taking place in between this Ti and T air. So we have to take here as a Ti minus T air. So this is the temperature. Now we will show the resistance. Now this resistance R1 and R2 is in series. So we will show here resistance R1 and R2 are in series. Now at the same time, when this resistance, that is heat transfer process, is taking place, then at the same time the heat transfer process through sphere is also taking place. So we have to show this R1 R2 is in parallel with R3 and R4. So R3 and R4 are in series. So we will show here that is in the parallel way. Here is R3 and here is R4. Now we will calculate resistances R1 and R2 through cylinder. So we will draw here the cross section, that is circular cross section. So this is the inside surface of the cylinder, which is having temperature Ti 400 Kelvin. So I will mention here this Ti 400 Kelvin, and this is the thickness of the glass, and this is the outside surface of the storage tank, that is for the circular cross section. So we have to mention here the radius R1. So what is the radius R1? That is 0.5 meter. Now this thickness is 20 millimeter. So 20 millimeter, that is 0.02 meter. So we have to add 0.5 plus 0.02. So R1 is equal to 0.5 meter and R2 is equal to 0.52 meter. So these are the radius R1 and R2, where conductivity K is given and the convective heat transfer coefficient H is also given. Now what are the formula that we have to use to calculate the resistance R1 when the conduction process through cylinder is taking place? So we have formula for the cylinder: ln R2 by R1 divided by 2 pi Lk, where ln term is available in calculator. So we have to take ln inside the bracket, 0.52 by 0.5 divided by 2 pi L 2 meter, and K is given 1.4. So answer is 2.229 into 10 raised to minus 3 Kelvin by watt. Now what is the formula? We have to calculate the resistance for the convective heat transfer. So here 1 divided by HA1. Now this is very important. So this outside surface is in contact with air, where the convective heat transfer process is taking place. So we have to take the area equal to, which is having radius R2. So we will take here 1 divided by H is given 50, and this area 2 pi R2L. So 2 pi multiplied by R2. So R2 is 0.52 multiplied by L, that is 2. So which is equal to 3.061 into 10 raised to minus 3 Kelvin by watt. So what is the total resistance of the cylinder for the heat transfer? That is R1 plus R2, because these two resistance are in series. So we have to take R1 plus R2. So 5.29 into 10 raised to minus 3 Kelvin by watt. Now we will calculate R3, that is the resistance for the conduction heat transfer through hemisphere. Now here we will use the formula for the complete sphere, because this R3 is for the two times, that is this R3 is for one hemisphere and this R3 is for second hemisphere. So we will use the formula to calculate R3 for the complete sphere, that is R2 minus R1 divided by 4 pi k R1 R2. So we already know what is the value for R1 and what is the value of R2. So same values for these cylinders and sphere. So we will use the value, and it is equal to 4.372 into 10 raised to minus 3 Kelvin by watt. Now we will calculate R4. Now R4 is the resistance for the convective heat transfer from this hemisphere. So this R4 is also two times, so we will use the formula for the complete sphere, that is for the convection heat transfer losses, that is 1 divided by HA. So what is the area for this total sphere? So if we observe, this air is in contact with this outer surface, and this outer surface is having radius R2. So we will use 4 pi R2 square. So if we calculate this, we will get 5.886 into 10 raised to minus 3 Kelvin by watt. Now this R3 and R4 is in series. So what is the total resistance in sphere? That is R3 plus R4, which is equal to 10.258 into 10 raised to minus 3 Kelvin by watt. If we observe the electrical analogous circuit, then R cylinder and R sphere both are in parallel. So how to calculate the resistance of the equivalent for this total loop? So we have formula, that is, so for resistance of equivalent loop, that is R equivalent loop. So for this we have formula 1 divided by R equivalent loop is equal to 1 divided by R cylinder plus 1 divided by R sphere. So when we put the value, so R cylinder is nothing but R1 plus R2 and R sphere is R3 plus R4. So when we find out this answer, then this answer is for 1 divided by R equivalent loop. So to calculate R equivalent loop, we have to take the inverse for this answer, for the solution of this whole right hand side. So R equivalent loop is equal to 3.49 into 10 raised to minus 3. Now we have to find out what is the heat transfer or what is the heat flow that is taking place from this inside surface to the ambient air. So we have to take the temperature difference, that is Ti minus T air divided by summation of R, that is total resistance for this loop, that is R equivalent loop. So when we put the values, then we will get the answer 28.65 into 10 raised to 3 watt.